In quality control, we make a point, whenever possible, of examining the data collected at a job site in the form of a graph or chart. Of course, it does take time to create a graph or chart from a collection of figures. You may ask why we are willing to lavish such effort on graph-making activities. The answer is that the human brain does a far better job of analyzing any given situation when presented with some type of graphic depiction. Even a small child can tell the difference between smiles and frowns on the face of an adult. If the adult makes an angry face, the child instinctively realizes that something is wrong and will immediately burst into tears. The most sophisticated computers in existence today still cannot tell the difference between a happy face and an angry one, yet even the smallest child can do so. Computers lack the human eye's remarkable capacity for perception and analysis. Quality control experts always try to make the optimum use of special human characteristics. Now let's look at some data that were actually collected at an ironworks in Hokkaido. The process of steelmaking begins with the heating of iron ore in a blast furnace. Coke and limestone are added to the ore, and blasts of air are forced into the furnace, causing pig iron to separate out from the impurities. Ironworks are always in competition to see how many tons of pig iron they can produce per furnace per day. In any case, data on the blast furnace at this particular factory were collected, and they formed a peculiar-looking graph. These data were gathered during the summer season, and as you can see, the daily pig iron output is fairly stable. We do see some dispersion, but the process is on the whole stable. The data collected in the winter, however, formed a very different kind of graph. Clearly, there were some days on which the output of pig iron suddenly dropped. What could be the meaning of this? Anyone can see just by looking at this graph that there was some abnormality in the process. Now, since this only happened in the winter time, it seemed that the wintry weather conditions might have some effect on production. The ironworks tried making additional graphs using all kinds of data on temperature changes and other weather conditions, and it finally found the culprit. It turned out that there had been snowstorms on every day on which pig iron output had dropped. Why was it that iron could not be made whenever snow was falling? To answer a question like this, it is necessary to check out the scene of the trouble. The QC experts waited for a day when there was a blizzard and went out to inspect the blast furnace. It didn't take long to figure out what was wrong. Pig iron production has changed over the years, but in those days the raw materials were loaded into large buckets and hauled up on a conveyor. If a snowstorm was in progress at the time, a layer of snow would accumulate on top of the contents of the bucket, creating an ice cream-like coating. With all that snow being dumped into the blast furnace, it was no wonder that not much pig iron could be produced on snowy days. All that had to be done to solve the problem was to cover the conveyor so that snow could not get in. Now let's take a look at some other data. The graph you see here is called a correlation chart. As you know, VTRs are selling very well these days. This graph plots annual income on the horizontal axis against rates of VTR purchase on the vertical axis. Common sense would seem to tell us that the higher the income, the greater the rate of VTR purchase, and this is true up to a certain point. When this point is surpassed, however, we find that the rate of purchase levels off and dispersion is observed. Thus we see that the likelihood of less well-off people buying a VTR increases in direct proportion to their incomes. The rate of purchase is of course high among the rich, but not everyone in the highest income bracket seems to want to own a VTR. From this we can infer that the rich have the leeway to enjoy all kinds of entertainments, and a VTR is just one of many options to them.
The correlation chart is a graph that comes in handy in testing for relationship between two sets of data. It is useful in studying relationships between a cause and effect, as well as those between two separate causes or effects. Now let's investigate the objectives and use of correlation charts.
日本人の背の高さについて
A number of interesting things can be learned from collecting data on personal heights. From time to time I travel overseas, and when I go to Northern Europe, I see so many tall and lanky people that I feel as though I'm walking through a forest of trees. Wondering what factors have bearing on height, I might consider drawing up a correlation chart. A correlation chart usually graphs causes on the horizontal axis against effects on the vertical axis. A certain elementary school in Japan prepared a correlation chart to study the relationship between children's heights and those of their fathers. Here is that chart in its completed form. Each of the points you see here represents an individual case. Height is of course affected by a number of factors, but as a general conclusion we can say that fathers who are tall also seem to have children who are tall. In our school days, we were all taught Mendel's laws of heredity, and judging from the results of this graph, the laws do seem to apply to height, at least to some extent. We must remember, however, that the height of the mother is not taken into consideration in this chart. There is therefore a certain degree of dispersion, but it is safe to say, just on the basis of the graph, that there is some relationship between the heights of parents and their children. This is the kind of inference we can draw from correlation charts.
The correlation chart is a graph made by plotting the values of two corresponding sets of data, one on the vertical axis and the other on the horizontal axis. The purpose of the correlation chart is to investigate the relationship between two kinds of data. When a relationship does exist, the chart can also be helpful in determining how causal factors can be manipulated to see that a certain effect falls within a standard range.
Let's look at another chart. This one shows the relationship between the measurements of neck circumference and neck-to-cuff length for ready-made men's shirts sold by a department store. In this graph, the vertical axis represents neck circumference and the horizontal axis neck-to-cuff length. A glance at this graph is enough to tell you that a neat relationship does seem to exist between these two dimensions. People having narrow necks tend to have short arms. A department store must of course sell its products and will not want to carry large numbers of shirts with unusual combinations of measurements. Thus we can infer from this correlation chart that there are not many people in the world who have very thick necks and short arms. We can also conclude from this chart that human bodies do not vary all that much in form. There is a limited number of physical types. Let's turn now to another chart. This chart was drawn up by a store selling household electrical appliances. Its aim was to study the relationship between the prices of stereo systems and the number of each type sold. The horizontal axis shows the prices for individual items, and the vertical axis shows how many units are sold per month. As we would expect, the higher the price, the smaller the number of stereos sold. And, as common sense will tell us, the lower price systems made for the popular market sell in large quantities. So, as you see, we write in the causal factor along the horizontal axis and place the effect on the vertical axis. When each of the points of correspondence between the two are plotted, we study the pattern formed by these points to determine what, if any, kind of relationship exists. This is the essence of the correlation chart.
Let's now learn how to prepare a correlation chart, taking as example the interrelation between children's and parents' heights. Collect a number of pairs of data to check for correlation. One of the data in each corresponding pair will become the X value and the other the Y value. When you are dealing with a cause and an effect, designate the causal factor X. You should try to collect at least 30 pairs of data. Determine the highest and lowest values for each pair of data x and y. Construct horizontal and vertical axes, making the horizontal axis x. Mark off the scales along each axis so that the distance between the highest and lowest value is about the same for x and y respectively. Plot the points where the values of x and y data intersect. Lastly, as necessary, write in the number of data, the term of data collection, the purpose of the graph, the name of the product or process, and the date of preparation. The points plotted on a correlation chart can cluster together to form various patterns, each with its own significance. In graph A on your screen, the value of y clearly increases as the value of x increases. In B, the value of y shows some tendency to increase as x grows larger. With a graph such as A or B, we say that there is a positive correlation. A graph that looks like C tells us that no relationship at all exists between x and y. We thus say that there is no correlation. In D, y shows some tendency to decrease in value as the value of x increases. And in E, we see y clearly decreasing in inverse proportion to x. When a graph looks like D or E, we say that a negative correlation exists between x and y. Test for the presence of correlation. Investigate unusually positioned points. Use in conjunction with stratification. Double-check the relationship between two data. Control charts demonstrate changes in the dispersion of data handled in a factory or elsewhere. They also indicate the cause of the dispersion. Let's see why and how control charts are made.
I think that by now you can see the importance of putting figures into graphic form in order to determine their significance. You will find that the same sets of figures can create very different patterns in separate graphs prepared in different ways. These various graphing methods can be likened to the diagnostic tests that are used to determine the causes of human illness, blood tests and X-ray photographs, for instance. Now please take a look at this histogram. Looking at this graph alone, we get the feeling that all is going smoothly. The histogram is symmetrical in form and the dispersion is not too wide. But if we use the same data to create a different type of graph, this one illustrating mean values and showing the passage of time along the horizontal axis, we see a completely different aspect of the same situation. Looking at this graph, we see at once that the average figures, on the whole, show a gradual tendency to rise. We can predict that they will continue to increase in this manner, eventually becoming too large to meet the standard if nothing is done to change the situation. We could not have learned this from the histogram that we saw earlier. Let's look at a chart made using real data gathered at a factory. Examining this chart, we see that a histogram has been drawn in at the far right of the chart. There is nothing much out of the ordinary about the histogram itself. But plotting daily figures in a broken line graph, we see that the values show a gradual tendency to increase at the right. Lines representing the Japan industrial standards are written in at the top and bottom of this graph, and it is clear that the values are all well within the standard range at the present time. But just because there is plenty of leeway doesn't mean that nothing will go wrong in the future. Now let's try something using the histogram appearing at the right of this chart. If we extend two lines straight across to the left, one from each end of the base of the histogram, we can create two new limiting lines. These new limits are more stringent than the Japan industrial standards, and we can see that the line formed by the values of the graph is apt to intersect the limiting line at any time. Insertion of these limiting lines makes it possible for us to judge whether or not something abnormal is occurring. Limit lines used for this purpose are known as control lines. A broken line graph on which control lines have been superimposed is generally called a control chart.
したがいまして、この折れ線グラフに管理限界線を入れたもの、これを私たちは普通管理図と呼んでいるわけです。
A control chart monitors the movement of data over time, making it possible to judge whether or not abnormalities are present. It takes the form of a broken line graph with control lines written in. The control chart is an aid to controlling a process. It points the way to accurate assessments, inquiry into actual causal factors, and the swift adoption of remedial measures.
This is a control chart for the pressing work done in a certain factory. As you can tell by looking at this chart, the mean values vary wildly. I would like you to pay special note, however, to the fact that the readings started out very good, remaining close to the center line at the beginning of the graph. But one day, the value suddenly plunged down beneath the lower limiting line, next rising sharply to pierce through the upper limit. It was then decided to look into what happened at the point in time where the value leaped. It turned out that that point in time coincided with the point at which the metal molds used in pressing work were changed. Sure enough, tracing the process back to the point where the mean value first dropped, this was also found to have occurred at the time when metal molds were replaced. The same was true of the next point at which the value suddenly soared. Once these observations were made, it became clear what needed to be done by way of remedy. The replacement molds had to be specially prepared for use so that the mean value would remain within control limits. Steps could now be taken to bring about improvement. Once remedial measures were taken, the mean values became fairly stable. We can see from the graph that they have continued to vary in an appropriate manner without intersecting the control limits at any point. Let's now look at a control chart used in a factory. This control chart represents thickness measurements for the joints or metal connectors you see here in this diagram. The tips of these joints must be made with great precision. Let's see what we can learn by looking at the control chart. Around the point where the graph begins, we see that the mean value of the measurement is extremely high. This was corrected at once, after which the readings remained within the standard limits. The dispersion also remained generally stable. Eventually, however, an abnormal value was once again registered. This was in the 21st lot. Here, the mean value suddenly soared at the same time that the dispersion widened. Steps were taken at once to correct the situation, but these remedial measures were not successful, and the situation was still unstable at the point where the control chart ended. The role of the control chart is to make it possible to see whether or not an abnormality has occurred somewhere along the line. Control charts also function to tell us at a glance whether the problem involves the mean value or the dispersion.
Let's learn how to make a simple control chart. There are several different kinds of control chart, but let's choose as example one of the commonest type. Some control charts deal with continuous data and others with enumerated data. The X bar R control chart that we are about to examine is used with continuous data and consists of an X bar control chart for mean values combined with an R control chart that indicates the range of the dispersion. In the data we are using, appropriate judgments cannot be made, nor measures taken unless the mean value and dispersion can both be examined together. The control chart presents the two together in an easy-to-read and contrast form. Care must be taken in the preparation of the datasheet as a preliminary step to control chart construction, since we will be looking at the variation of data over time. When making an X bar R control chart, arrange the data in subgroups according to the day and time of measurement. Calculate and record on your data sheet the mean value and range for each subgroup as well as the overall mean and the average value for the range. Plot the mean values and range values on graph paper to create broken line graphs for both the X bar and R control charts. Compute the positions of the control limit lines based on the overall mean value for the subgroups and the average value for the range. Draw in control lines on both the X bar and R control charts. Use the formulas you see on your screen to determine the positions of these control lines. As a final step, when necessary, record additional information such as the size of each subgroup. Clearly define your objectives. Make the control chart a continuous study. Stratify your data. Construct the chart so that it can be easily understood by all.
The concept of control limits that we see in control charts is really a very good idea. As previously stated, control lines show the limits within which the values recorded will remain when the process is proceeding normally. Thus, the people responsible for management of the factory can feel assured that all is going well as long as the data collected remain within those limits. Special measures need only be taken when a reading goes beyond one of the limits. Actually, we often encounter this way of thinking in everyday life. A father with a young daughter will worry above all else that she may get romantically involved with some undesirable character. What he may do is monitor her comings and goings, taking note of what time she returns at night. If she usually gets in by 10, then he'll feel at ease as long as she returns around that time. If she one evening returns in the middle of the night, then the father might conclude that he's got a problem. We can say in this case that the control limit line the father has been using is 10 p.m. This common sense concept that we use all the time almost unconsciously is very skillfully incorporated into the workings of the control chart. Even when the graph data values are safely within the control limits, it is very easy to see in which direction they are headed. As you know, when we exercise quality control, we make an all-out search for the causal factors that lie behind defects. Then, one by one, we tackle these causal factors in pursuit of improvement. The tools of quality control are of great assistance to us in these efforts. But once we have set the factory or other processes on track, we will want to make sure that the process is normal and everything really is going as planned. Control charts are generally used as a kind of final check to determine the degree of our success.
というのが一般的なやり方なんです。